At the Technical University of Vienna, and this is my architectural diploma project, which I'm still currently working on. It's titled Order, a Space Station for Orbital Debris Recycling. So I'm sure many of you are aware of the risks and dangers of space debris. Nevertheless, I will give a quick overview of the topic. So by definition, any artificial object in space without a function is considered space debris. And to give you a number, we currently have around 2,000 satellites orbiting around us, but we're tracking up to 20,000 artificial objects in the proximity of our planet. And those are just the ones large enough to track. So space debris is usually the result of spent rocket stages or deactivated satellites, either still intact or breaking apart after years in orbit. And a widely accepted categorization is one by size. So the number I gave before only refers to large debris. Medium debris ranges from 1 to 10 centimeters, and there are an estimated amount of 750,000 in orbit. And small debris ranges from 1 to 10 millimeters, with an estimated amount of 166 million debris in orbit. Due to their high velocities, any of those objects pose a risk to current and future space missions. On the pictures here, we see the 2009 collision between two satellites, and that resulted in over 2,000 new large debris pieces. And it is also believed to be the starting point of the Kessler syndrome, which is a scenario already proposed in the late 70s by Donald J. Kessler, and suggests that once the debris density in low Earth orbit reaches a certain threshold, that resulting fragments from one collision will inevitably lead to further collisions in a cascading manner. So eventually resulting in a debris cloud so dense that it would render our satellite networks ineffective and make future spaceflight attempts nearly impossible. So it is a real threat, and the debris population is constantly growing, and studies suggest that at least 5 to 10 large debris pieces should be removed per year to ensure a stable environment. These are some of my early sketches for the project. The concept idea was to have a space station with a huge hangar to collect debris and salvage material from it, and surrounded by a habitation space for the crew. Also later on, this hangar space could be used to assemble spacecraft in orbit, utilizing the obtained material. For the mission design, the first step was to define a target debris, and I chose rocket bodies, specifically the Cosmos 3M and the Zenit 2 second stages. They have a high potential to contribute to the future debris population, and are also located in orbital inclinations close to one another. And also their high number and large mass and their material composition, which is mostly aluminum and steel, makes them a very good target for recycling. The capture method I chose would be a robotic arm attached to an ATV vehicle. Both are already well-developed technologies and reliable, and it would also be a valuable asset to have a spacecraft with a robotic arm attached for the assembly step of the space station. And there are two options how the station can capture debris. The first one would be that the ATV undocks from the station, raises altitude, and rendezvous with the target, then captures it and returns it to the station. And the station will be orbiting in LEO at a height of 400 to 600 kilometers to minimize the radiation hazard for the crew. Thank you. And it can capture debris at this height, at this altitude range by itself, using one of its own robotic arms. The next step was thinking about the construction. So the most challenging component for the station would be the hangar, since it has to contain at least one of the rocket bodies previously defined and leave maneuvering space around it. So this suggests either a partial or a complete assembly in orbit due to the current fairing size limitations. The company Made in Space, which you might have heard of, it's already the front runner for space-based additive manufacturing, and they teamed up with NASA recently to create the Archinaut, which is going to be a robotic spacecraft that can manufacture and assemble large structures in orbit, solely relying on material being fed to it. It would be a great asset for the station because it could construct the main truss work and also the hangar without any size limitations. And this is the intended material cycle. So after the station begins operation, it captures rocket stages, They then get disassembled in the hangar and the work module until you have fine metal chunks or pieces or flakes that are then fed into furnaces heated by parabolic mirrors at the extremities of the station. At their specific melting points, each of the metals gets sucked out of the furnace and pulverized. This results in an automatic material separation, and the pulverized material then gets filled into containers, creating feedstock replenishment that can be used by the Archinaut robots or the 3D printers on board, either to expand the station with further hangars or print spare parts or tool heads for the robotic arms. So let's take a look at the architecture itself. This is the current version of the project, and these are the components. So hindmost we see the modified ATV spacecraft. The blue module is the habitation module that can house a crew of 2 to 4. The red components are the work module with the airlock, and followed by the hangar. And on the port and starboard side we have the parabolic mirrors that are attached to huge rotators that can turn them around the pipeline system and the furnaces that are directly connected to the work module. Also attached to these parabolic mirrors are the solar panels and the radiators. The hangar itself is an extruded hexagon in shape, and it's a truss framework filled in with honeycomb aluminum plates. The truss framework can be used by the robotic arms for maneuvering, and they store the captured rocket bodies on the exterior sides of the hangar. Only one rocket body at a time is moved inside to the hangar to be processed. And the hangar itself is not pressurized, so due to the large amount of air that would be lost every time you bring in a new rocket body. Due to this fact, however, you have to, all the disintegration and sorting steps have to be done by robotic arms. So here, the rough processing begins, so the robots cut up and disassemble the rocket body, and they can either store the pieces internally on the hangar sides or directly move them into the airlock that, for further processing in the work module, which we see here on the left side. And this is a closer look of the work module. First, the airlock has 3 exits. One goes into the hangar itself, the other to the work module, and there is a third exit to the hangar's exterior used for crew EVA missions. And on top of the module we see the robot control cupola, which gives a great overview of the hangar's interior space. And on the side we see the toolhead exchange, which are basically a lot of small airlocks connected to the inside of the module, where the robotic arms can come and change their toolheads, either when they're worn off or if they need to perform a different task. And they can be picked up by the internal crew and quickly refurbished or changed out. And on the bottom we see the pipelines running to the furnaces and the parabolic mirrors. This is a section through the work module. So below the robot control cupola we see the workshop. Here the robotic arms and the toolheads can be repaired or refurbished. And in the bottom section we see the material processing part of the module. The 3D printers are located here, and also the fine processing racks, which are directly connected to the pipeline system. The habitation module is based on the transhab or the inflatable designs from Bigelow, and at the center of it lies a safe haven for high radiation events. It's accessible by 2 hatches on top and bottom and can house up to 4 people. And it's surrounded by a corridor of 1.50 meters in height. So this gives access to all of the module's areas and also provides space for sports or game activities. The module itself is separated into 3 parts. On the top we have, so on the top part we have the private quarters of the crew, the hygiene area and the restroom, and also the galley. So this would be here. In the middle part we have the storage section of the module, the safe haven, and the dining and conferencing table. And in the bottom part we have the waste storage, the life support systems, and the sports area. It's noteworthy maybe that the galley, the restroom, and the dining table, as well as the sports area, they all have a window that faces towards Earth all the time, so the crew is provided with a pleasant view. For the private quarters, it was important for me to encourage variability. So each crew member can quickly rearrange their quarter to their individual taste and add or remove storage units, replace the sleeping bag, move the workstation. Yeah, this helps to generate a sort of private feeling or a habitable feeling for the crew, and also helps to break monotony on long duration station missions. Here we see the galley and the sports area opening up towards the dining table. It can seat 4 persons and contains a screen and a projector for conferencing or movies that can be then processed by the crew. The screen is pulled down over one of the entrances to the storage units. And just as last, the assembly steps. So you would start with the modified ATV connected to a 6-way node, and then launch the habitation module and the work module, attach the airlock, and deploy the first Archinote robots that then would start to print the truss framework. Then you would add the solar panels and the radiators and begin the framework construction of the hangar, and the first robotic arms would be deployed. Then you add the first parabolic mirror segments, relocate the solar panels and radiators, and begin covering the hangar structure with aluminum plates. This is the station at its operational state, and this would be the station after a few years have passed and enough material has been salvaged, so it can utilize the material to add more hangars for more and different types of material processing. Thank you.
So how much, this is great, how much material is required to bring up at first to get started for minimal functionality?
That's a good question. I didn't actually calculate it through. You would build, the only thing that would be assembled in space is the truss framework and the hangar framework, but I have no real answer of how much material that would be. I have to go through that, but thank you.
Thanks.
Other questions in the back?
Yeah.
It's a quite nice concept.
Thank you.
Did you, considering that you will need lots of propellant to drag all the rocket bodies to your space station, have you considered extracting residual fuel from the rocket bodies and storing it and processing like you do with the solid materials, but also like the liquid package?
It was actually an idea. I didn't mention it before here. So what's also important is to rid all the rocket bodies of residue fuel, because if you start drilling around on them and disintegrating them, it's a huge risk. But I was not sure if you could, like, if there's different types of fuel and if you could just combine it to one source fuel. So it would be a nice idea to collect the fuel of the. You definitely have to remove it before, so actually you could collect it and use it for the ATV to. Yeah.
Okay, thanks, Ethan. So I realize there's more questions. I'm sure you'll be available after the session. We're going to press on because we'll go on.
I also have one question.
And I have one too.
Yeah, so we're going to hold on it.
So don't disappear at the end of the session.
Okay. Thank you.
Okay, thank you.